words, we need to compute dy dx. So what is dy dx? Well, that's the whole thing we did over there, right? Dy dx is dy dt over dx dt. And what's dy dt?
3t squared minus 3.
3t squared minus 3. And what is dx dt?
2t.
Something smelly, something smelly. Can you put that away? It smells.
What's dx dt? 2t. Okay, so that wasn't too hard. Here is a formula. What is this formula in words? Or I'll just tell you. This is a formula which tells me for a particular t value what the slope of the tangent line to the curve is at that particular point. Cool? Okay, so where are we interested in the slope? Root 3 at t equals root 3. Yeah. So in other words, I say, okay, well, what is dy dx at t equals root 3? And that's what this formula is good for, right? It means you can just plug in a t value and it will tell you the slope. Okay, everyone do it? Kind of on the fast side. I got 6 over 2 root 3, cool? So that's 3 over root 3, so that's actually just root 3. Good? Say good. Okay, and what is dy dx at, what's the other time I care about things?
Negative root 3.
Exactly, at t equals negative root 3. So again, I just have a number, a t value, I just plug it into the formula, and it will give me 6 over negative 2 root 3. So that's just negative root 3. Everyone good? All right, so I know the slope and I already knew the point. So I claim that this line must be the line y equals root 3 x minus 3. Because it goes to the point 3 comma 0 and it has slope root 3. Agree? And this line, the other line must be y equals negative root 3 x minus 3. Okay, cool. Memarize, can you get that red marker? So what that tells me is, this is going to help me ultimately make the make the picture. Is that I have a slope at as t comes up from down here at time negative root 3. I'm going to have a line with slope negative root 3, and at time root 3, I'm going to have a line with slope root 3. So I'm just drawing in tangent lines. Okay, here's another thing that calculus can tell us. Where do we have horizontal tangent lines? So I'll just say horizontal tangents.
dy dx equals 0.
Yeah, of course I'm going to have a horizontal tangent whenever dy dx is 0. When's that going to happen? Yeah, so I'm going to have a horizontal tangent whenever that numerator is 0. So in other words, whenever 3t squared minus 3 is 0, which is going to happen at, and also negative 1. Yeah, at t equals plus or minus 1, right? Because it's when t squared is 1, good? Okay, so where am I at t equals 1? At t equals 1, where am I? 1 comma negative 2. And where am I at t equals negative 1? It's going to be 1 comma 2. If I plug negative 1 into that formula, I get 2. Okay, cool. So this tells me that up here, then I'm going to have this point, this point 1 comma 2. And when am I going to be at 1 comma 2? At t equals negative 1. And that there is going to be a horizontal tangent there. So I'm sort of like, boom. And I also know that I'm going to be at the point 1 comma negative 2, 1 comma negative 2, at t equals positive 1. and also that there'll be a horizontal tangent there. Okay, when am I going to have a vertical tangent? Yeah, I'm going to have a vertical tangent when the slope is like infinite, right? Which is another way of saying that dx dt is 0. And when is dx dt 0? Only when t equals 0. So the answer is at t equals 0, which, as we already know, is 0, 0. Okay, so continuing to kind of add information to my picture, I'm going to draw like a horizontal or a vertical tangent at 0, 0, in addition to my horizontal tangents there. And now this Jesus fish is starting to come into shape, right? So I think this is turning out to be pretty much correct. There's one thing left that we don't know, that we're going to run out of time. Concavity. So what I want to know is this thing concave up or concave down? So what I need to know is, at what rate is dy dx changing with respect to x? So I want to know, what is the derivative with respect to x of dy dx? And notice that I am asking with respect to x, right? Because I don't really care about t per se. What I'm asking is, when my tangent is a certain spot, what does that tangent line do when I scoot over a little bit in the positive direction? Okay, this is the part that people find sort of tricky, because, well, okay, I have some notes on this, so maybe I'll just wing it. So I need to find the derivative with respect to x of dy dx, right? So in other words, but dy dx, like, just is some function of t. So maybe just temporarily, just call like dy dx like z or something. I wrote this down in a way that people liked or not. Yeah. So yeah. Okay. So if I call this z, then what I'm really saying is, what is the derivative with respect to x of this like z thing? And really that's just like dz dx. In other words, I'm asking for what is the rate of change of dy dx, which I'm calling z, with respect to x. Well, now notice this is just another example of the thing we did at the beginning of class. And so what is dz dx? It's dz dt over dx dt. And so if I really want to find the rate of change with respect to x of the rate of change of y with respect to x, then I need to take the derivative with respect to t of dy dx over dx dt. Okay, so for this problem over here, I have already calculated that dy dx is 3t squared minus 3 over 2t. That I already know. What I want to know now is, how is that changing over time? And the answer is, it's the derivative with respect to t of that whole thing over dx dt. Which is just 2t. Okay, we're running out of time, so I'm just going to tell you the answer to this. Oh no, I didn't even write it down. I think the answer is, oh crap, I guess I have to do it really fast. So I'm going to do the quotient rule up here. So it's the root of the top times the bottom minus the top times the derivative of the bottom, hang on one second, over the bottom squared, and then all over another 2t. So what do we end up with? We end up with 8t squared minus 6t squared plus 6, 12? 12. 12t squared minus 6t squared plus 6 all over 8t cubed, I think. So that's 6t squared plus 6 all over 8t cubed. All right, yeah, that looks familiar. That tells me, that is a formula for the rate at which the thing is changing. So now if I make a sign chart for this, the numerator is always positive and the Denominator changes sign from negative to positive at 0. So this is negative positive. Conclusion. This is concave down and then concave up. All right, so finally, we just draw the picture, including all of those things. I know the horizontal tangents are, I know where the vertical tangents are, I know it's concave, so I start down here at negative infinity, crossing the point 3, 0 with slope negative root 3, concave down, still concave down, vertical or horizontal tangent, vertical tangent, now it changes to concave up, and we get a bit of this, and a little bit of that. Ta-da! That is, so it was a Jesus fish after all. This was t equals negative infinity. Arrows, arrows, arrows. Okay, go to your next class, Ryan, show, turn it off. That's how you graph parametric groups and calculus. Bye.